Hi, I'm Connor from the computational music team, and I'm excited to introduce you to a framework called Music Understanding. It gives you access to on-device musical intelligence across all Apple platforms. It handles all the signal processing and model inference for you, so you don't need any expertise in signal processing or machine learning to use it. And because it runs entirely on device, the audio you analyze stays private and works offline. At Apple, the Final Cut Pro team used the Music Understanding framework to power 2 features of their app. In the beat detection feature, Final Cut Pro analyzes a song for its rhythm and structure to reveal its beat grid. This helps editors visualize and align their edits to song parts, bars, and beats. And in Final Cut Pro for iPad, the montage feature analyzes for rhythm, pace, and structure to automatically synchronize clips to the music. I'll start by going over what the framework can do. Then, I'll follow that up by explaining how you can use the framework. Finally, I'll go through the API and show how it was used to build a sample app for understanding music. The framework provides analysis around 6 main areas: key, rhythm, structure, pace, instrument activity, and loudness. Rhythm is the pulse of a song driven by individual beats. These beats build into bars. The number of beats in 1 minute is called beats per minute, or BPM. Bars form phrases, which you can think of as musical sentences. Phrases combine into segments, creating a more complete musical statement. And those segments ultimately build the sections. You can think of a section as a chorus, verse, intro, or bridge. During a song, instruments such as a drum, bass, or vocals may be playing at different times and at different intensities. These instruments play around a common set of notes called the key. While the song may have a consistent pulse, or BPM, different parts of the song may feel slower or faster. This is called pace. Over time, the song may sound louder at some points than others. These are the building blocks of the Music Understanding framework. And by integrating it in your app, you unlock a whole new level of possibilities. Next, I'll talk about how to use the framework. At a high level, apps interact with a music understanding session, initializing with either an AV asset or a custom audio provider. To start analysis, clients call Analyze and await results. By default, the framework analyzes for all analysis types. For the highest performance, you can specify which analysis types you are interested in to avoid unnecessary computations. To explore the framework more deeply, I'll review a sample app called Music Understanding Lab, available on developer.apple.com. Let me show you how Music Understanding Lab works. First, I'll select a song on the device. The app uses the Music Understanding framework to analyze the audio, turning it into a visual experience with a dedicated tile for each result. When I hit play, notice the rhythm and structure tiles update as the song plays. The playhead ties the experience together, letting you follow along with the music. I'll start by talking about how the Select Song button is implemented. Using the SwiftUI file importer, I'll select a file to get its URL. Then, I'll use that URL to create an AV URL asset. Be sure to set prefer precise duration and timing key to true to ensure the most accurate results. Next, I'll create the session from the asset and call analyze and await the return of the session results. Inside the session results struct, every feature Music Understanding analyzes gets its own results field. These are all optionals. When you use the general Analyze API, all results will be available. However, if you use the targeted Analyze For API, the framework will only return the results you asked for, and the rest will be nil. Throughout the Music Understanding framework, there are two standard types used to associate time with a value. A timed value associates a value with a CM time. Similar to time value, a ranged value associates a CM time range with a value. With these time-based types in mind, I'll discuss the features Music Understanding analyzes by showing how they are used in the Music Understanding Lab UI. First, I'm going to start with the key tile. In this song, the musical key is D flat major. For key analysis, the Music Understanding framework returns a key result struct. The result contains an array of ranges, mapping a key signature to a specific time range using a ranged value. A key signature contains a tonic and a mode. A tonic can be any of the standard chromatic pitches. It represents the root note, like C or G, around which the song is built. And the mode, which is either major or minor. Next to key is the rhythm tile. The tile displays BPM on the left and indicators on the right that light up as each beat plays. When you analyze for rhythm, you get back a rhythm result. In this struct, Music Understanding gives you the timestamps for every beat and bar as arrays of CM time. The framework also provides the overall global tempo with beats per minute. Notice, BPM is optional. That's because if the framework hasn't processed enough audio to find at least 2 beats, the BPM will be set to nil. Now, I'm going to talk about the structure tile. In the tile, there are 3 rows of rectangles that indicate a song's structural hierarchy. Each rectangle is a time range in the song. Music Understanding supports 3 levels of structure: sections, segments, and phrases. The top row represents sections of a song. Each block shows the time range of a section. Each section is made up of 1 or more segments, which appear below the section rectangles. And each segment is made up of phrases. During playback, the current section, segment, and phrase appear highlighted. When you request structure analysis, the framework returns structure result. It has 3 properties for sections, segments, and phrases. For each of these, you get an array of CM time ranges. The next tile is pace. It tells you how fast the music feels to the listener. Parts of a song that feel faster or more energetic will have a higher value compared to slower or less energetic parts. In this UI, taller bars represent higher energy, while shorter bars represent lower energy. When you request pace analysis, you get back a pace result. The struct has a single property containing an array of ranged values. Next, I'll talk about the instrument activity tiles. Music Understanding Lab displays several tiles that visualize instrument activity, either as time ranges, where color-coded bars indicate the active instruments present, or as a detailed activity graph. The graph plots values between 0 and 1, representing the strength of each instrument. The closer the value is to 1, the louder the instrument is in the mix. When you request instrument activity, the framework returns an instrument activity result. It has two properties, one for ranges and one for activity. The Ranges API provides a dictionary mapping each instrument to an array of CM time ranges. This is great for situations where you just want to know if an instrument is present or not. But sometimes you need more detail, and activity provides that. Activity maps an instrument to a time value of floats. The activity results express how intensely an instrument is playing over time and is a great source to drive audio-reactive animations. The loudness tile appears below instrument activity. The framework provides measurements in loudness units full scale, or loose, which is the industry standard for modeling how the human ear perceives volume. At the top of the tile is a single integrated loudness value, which gives the average loudness for the whole song. Below that is a graph of momentary loudness, showing how loudness varies over time. The framework also provides a peak value, which describes the absolute highest audio volume in decibels. When you request loudness analysis, the framework returns a loudness result struct. Music Understanding supports integrated, momentary, and short-term loudness. Integrated provides a single value that represents the overall loudness of the audio. Momentary and short-term provide timestamp values every 100 milliseconds. Momentary values are calculated over a window of 400 milliseconds. They are useful to detect short, sudden spikes in loudness. Short-term values are calculated over a window of 3 seconds, which provides a smoother view of the loudness trend over time. The peak value tells you exactly where the track hits its maximum level and is measured in decibels. Music Understanding Session also provides a streaming API for loudness. Values are delivered via an ASIC sequence for every 100 milliseconds of audio analyzed by the framework. Here's an example of how it can be used. I'll initialize the session as I did previously, but this time I'll set up two tasks. One, to consume loudness results as they are delivered, and another to begin the analysis. Now, I'll talk about the audio provider in this example. An audio provider conforms to ASIC sequence and yields AV read-only audio PCM buffer objects. When the audio provider has set all audio buffers, it must send a final nil to signal completion. I'd like to focus now on the two icons at the top of Music Understanding Lab. At the far right, there is a Share button. When you tap it, a JSON file is exported with all analysis data. All Music Understanding results are codable. To encode to JSON, just create a JSON encoder and encode the session results. A button with a film strip icon appears next to the Export button. When tapped, it opens the Video tile. The Video tile uses structure and pace to create a video synced to the music. I'll talk about how it works. The Video tile displays a series of video clips that match the feeling of the music. The algorithm starts by identifying the song section time ranges. Then, it uses the pace of each section to determine how many clips to display in that time range. Since pace is an event per minute rate, it can be divided by 60 seconds to determine the time per clip. This produces clips that always begin at the start of each section, and the clips within a section match the energy of the song. I then use this timing information to construct a video synced to the music. The video clips are retimed to match the target clip duration, with longer, slower clips during the less energetic parts, and shorter, faster clips during the more energetic parts. This overview gives you a sense of how these APIs work together in practice. With these basics covered, you are ready to dive in. With music understanding, you can sync visuals to the beat, loudness, or pace of a song to build powerful video editing features. Organize music catalogs by tempo or key to drive a DJ app. Or pre-compute and bundle analysis data to animate your game to music. Check out the Music Understanding Framework documentation on developer.apple.com and download Music Understanding Lab to help kickstart development of your own applications. This technology was built to solve real challenges here at Apple. The ideas were there, but the tools to build them were not. These tools are now in your hands. Make something awesome. Thanks for watching.